It's the other way around, right? Yes. So in fact, we said that it's the right movers that depend on sigma minus, right? So this is different from 0, and we found a solution for this. Or we expanded in Taylor, in Fourier modes. We expanded, we said this is periodic in sigma, so we can expand it. And this is what we got. And the other one was also periodic in sigma, and the Fourier modes are given by alpha tilde, okay? Well, you see, if you look at the reason for the name comes from these pieces, right? This is the only part where it makes a difference. And you see that what you can think about sigma as being an angular variable, right? It goes from 0 to pi. And the 2, well, we could have included that in the definition of the length. So it would have gone from 0 to 2 pi. And then you see that the difference in sign would tell you that one of them goes in one direction and the other one goes in the opposite direction as you go from 0 to pi, okay? So that's the reason for the name right and left movers in terms of how they move, how these solutions behave. Yes? No, forward and backward would be a little bit funny because this is a circle.
Right.
So you have right. So you have, well, it could be clockwise and anti-clockwise, but that would be too long.
Okay.
So here is your proposal is to collect XA. Yeah. Okay, very good. Now, right. So what do we want to do? So today, we want to continue. Hopefully, yeah, the plan is today to get to start the quantization of the string. That's where the fun will start. At the moment, everything we have done looks very nice, and there is almost nothing interesting about the number of scalar fields that we have on the wall sheet. Okay, so in fact, this classical solution is there for any number of scalar fields. By scalar fields, I mean x, and therefore any space-time dimension. Okay, but now to move forward, we have to study the conserved charges in the system. Okay, and for that we have to use Noether's theorem, which of course I'm sure this is the 100th time that you probably have seen that or that you have used it. And that's the reason why we're not going to do it in detail. We're just going to remind you, or I'm going to remind you what happens. Remember, for every global symmetry, we can produce a current. So let's call it J. A current is something that has a vector index, right? Since we are dealing with a field theory in 2 dimensions, whatever current we have will have a vector index on the wall sheet. And remember, we decided to use the convention that the vector index on the wall sheet, or those will be called alpha, right? So alpha goes from 0 to 1. So this is a vector on the wall sheet, and this is the index that we're using there. Now, once you have a current, this is not any current. This is a conserved current. What does it mean that it's conserved? Well, it means that this is satisfied. Once you have a conserved current, you can produce a conserved charge. And how do you do that from the current? Anyone? Can remind us? Very good. So you define the charge by integrating the zeroth component over all the space direction. In this case, we're going to get an integration over sigma. And the reason this is conserved is that if you take a derivative with respect to time, so that's what you want to show it's 0, that's what it means that it's conserved, that as time evolves, this quantity doesn't change in time. So you pass that here, you get a derivative, a partial derivative with respect to time. You use this equation, becomes a derivative with respect to sigma. And then if the space is non-compact and the fields decay nicely at infinity, you get 0. Would that happen in our case? Well, let's see what kind of current can we get. What are the global symmetries we have? Well, we said we can change our scalar fields by a constant. If we shift everybody by a constant, then this is a symmetry of our action. Therefore, how many symmetries we have? Well, in fact, we have one per scalar field. So this index mu is now something that labels all the different shifts that I can do, right? So I can do one per scalar field. So this index is an index that tells us the different shifts we can make on the different scalar fields. So these are, if you wish, different symmetries, okay? So for each of them, we should get a current, right? So from this symmetry, we're going to get a current. So we have to find a name for that current. In principle, we could call it J, alpha, and for each one of them, we will get one current. So there is this index mu. But I'm not going to use this notation because there will be several symmetries, right? So there are more global symmetries. And we cannot keep using J all the time. Since this is related to translations in space, in the target space, maybe it's a good notation to call it P. So this is just a notation. Just going to call the current P. It has the index alpha because it's a vector on the wall sheet, and it has an index mu because I have one per target space dimension. Okay? Very good. So now you can go ahead and use Noether's theorem to compute what this current is from our action. So let's write it here. So you can go ahead and do it. I think you will do it today in the tutorial. And you will find something that looks like T times x dot mu. Sorry. This is what you will find. Okay? Very good. So those are the currents associated to this global symmetry. Now let's compute the charge. Well, for lack of imagination, I'm going to call the charge. I'm not going to call it Q mu, as I could have. So I could call the charge Q mu, but I'm not going to call it like that. I'm going to call it P mu. So the charge, according to my definition, should be an integral over our spatial directions of the zeroth component of the current. So that would be x dot mu. Okay? So this is just T. Now here comes the question. Is this conserved? Why is it conserved? No, remember. Oh, that's something very important that you should keep in mind. Not every time you have a conserved current, you will have a conserved charge. There are cases in field theory where you have a conserved current, and then when you try to compute the charge, remember the proof uses the fact that you have to use a Stokes theorem to get something to get the integral at infinity. If the fields don't vanish fast enough at infinity, or there is something funny at infinity, or there is no infinity, right? Like in this case, you have to worry about those cases, right? So in this case, we don't have infinity. So if we want to show that this is actually conserved, we will have to do some work. So we can take the derivative with respect to tau, and then we will get something like 0 to pi d sigma. This will come in as a partial derivative. So this thing will be x double dot mu. But now we can use the equations of motion and replace this by double prime using the equations of motion. And one of these derivatives, we can use it to write this as x prime. Prime, let me remind you, we had this notation. Yep. Just because I'm a little bit too lazy. Okay, sorry. Yeah, I'm doing things that I'm not supposed to be doing. Using the equations of motion, this is equivalent to x double prime. Right? Not supposed to be erasing them. Okay, so we get this thing. So we can use one of the derivatives to carry out the integration, and we get t of x mu as sigma equals to pi minus x mu as sigma equals to 0. But now we see that this is 0 for our closed stream because it's periodic. So the two contributions cancel, and we get 0. If we had done the same thing for the open stream, then we would have found that this vanishes only when we have Neumann boundary conditions on both sides. If we have Dirichlet, it wouldn't have worked. What's the physical reason why it wouldn't have worked?
Because you have to be, it cannot be conserved because it's restricted to moving the ray.
Right. So is that what you had? It's attached to something. So that something can actually provide momentum or take momentum from the string. So it doesn't have to be conserved. Okay. Very good. Okay. But now we're doing the closed string, so we can just go ahead and compute what this thing is by using our explicit mode expansion. Okay. So all the oscillators will contribute nothing to this, because they basically integrate to 0 when we go from 0 to pi. So if we use that formula, we'll get that P mu only receives contribution from the second term. The first one vanishes, or the center of mass of the stream vanishes because it doesn't depend on tau. And we're taking the tau derivative. So we simply get 2 times the string length times t coming from the definition times alpha 0 mu. Okay? So from here, we get a nice interpretation for our 0 mode. Something of the form, well, not quite, right? Because I still have to do the integration from 0 to pi. So you get a factor of pi here, coming from the integration from 0 to pi of just 1, because nothing depends on sigma. So I should remember to put the pi here. Okay. Very good. Now, I think that also in the tutorial, this is something that will be useful tomorrow, so it's good if you do it today. In the tutorial, you will also study what happens under a transformation of this form. Remember, this is a Lorentz transformation. in the target space. Now, in this case, you will have many, many currents, right? They are actually labeled by 2 indices. Here it's natural to call them J mu nu. And you will find that they are given by something that looks like, I can do something like x mu del alpha x nu minus x nu del alpha x mu. Okay? And then following the same idea, you can compute the conserved charges. Okay? Now you see the interpretation of these ones. The interpretations of these ones are precisely the angular momentum charges in space-time, in the target space. Okay? Very good. I think now we can use this. Now we want to go back and, well, we found all the solutions of the equations of motions consistent with the boundary conditions. But remember, we got this as solutions of this action. But this is not the full physical story. Remember, this action is the action we got by gauge fixing the wall sheet metric. So in order to have the full physical picture, we also have to remember to impose the constraints. Which were coming from the vanishing, asking the vanishing of the energy momentum tensor. And the constraints, last time, we showed that they were given by something like this. Can anyone very quickly remind us what's the meaning of all the dots and the primes here? So what's the meaning of this dot? Excellent. This one? Excellent. And this one? Okay, very good. So we're on the same page. So yeah, it's important to know what, to remember what we're writing. Okay, so is there any nice way of writing these constraints, which involve derivatives with respect to sigma and tau, in a way that will have a connection to the new coordinates we introduced, sigma plus and sigma minus? Remember, it was only in terms of sigma plus and sigma minus that we got nice decompositions into the left and the right movers. Well, this formula and this formula somehow are begging you to be combined, right? Something like this. You have this is equal to 0. Then why not add the other one with a plus minus here and 2 times? That's what it wants you to do, right? Once you do that, then you get something that looks like this. And therefore, you get sigma plus of x squared is equal to 0, and sigma minus of x squared must be 0. So those are the new constraints. And they look very nice because now we can use that only the left movers contribute to this and only the right movers contribute to this. In fact, we found the expansions in Fourier modes of these guys and these guys even before we did it for x. That's the way we found the expansion for x. So we can go back and try to compute these things in terms of oscillators. But of course, these quantities themselves are periodic. So this and this they are periodic in sigma. So why not decompose them in Fourier modes as we did for the individual ones, okay? Here we're going to decompose them in Fourier modes because then it's going to be easier to impose the constraints. You just have to impose that every mode has to be 0 instead of imposing a complicated quadratic relation between the original modes, okay? So let me get my conventions straight. So we're going to call, let's see, it's plus, right. So once again, we're going to have Fourier modes, sigma plus, and the name we're going to give to the modes is LM tilde. So I hope I'm consistent. So if we have sigma plus has a tilde, very good. So I want to be consistent with the tildes. Once again, this has dimensions in space-time of length square, so it's nice to introduce a string length square here to compensate for the dimensions so that these guys will be dimensionless. Likewise, we're going to expand these ones. In Fourier modes, okay?
Can you tell me how these two equations show us that this XL is periodic in sigma?
Well, we know, the first thing we know is that X is periodic in sigma, right? That's what we chose as boundary condition, right? So that's a closed string. So if this is periodic in sigma, then the derivative with respect to sigma plus and the derivative with respect to sigma minus is also a periodic function of sigma. Okay. Yes?
Isn't the derivative dimensionless?
Yes, but I'm compensating for the dimensions of x squared. Right? I want to interpret x as a length, as x as a coordinate in space in space-time, in the target space. Yes?
Maybe it's not a question, but you square the expression and your exponent still has minus 2im sigma plus.
Very, very good question. Yes, I'm saying this object is periodic. So whatever it is, a cube, I could put this to the 100th and say this is periodic in sigma. So it has a Fourier decomposition. And the Fourier decomposition involves all modes. Okay? Now, I think it's going to get a little bit clearer. Yeah, the L squared is dimensional analysis, right? Because I want this guy to carry dimensions of length, and I want the L's to be dimensionless. Therefore, I should put an L squared there. Right? The 2 is just convention. Now, it's going to be even better once we decide to write these guys in terms of the original oscillators. So how do we do that? Well, we have to plug that expression for x in this formula. And if we want to compute this LM, the way to do it would be the following. You can take this guy here. You can multiply by e to the 2in sigma plus, say. Well, in fact, we can do the following. If we want to compute these LMs, we can set tau to 0. Well, I should actually be more systematic here. So we want to compute as a function of the alpha tildes. So the first thing is to set tau equals to 0, right? All the tau dependencies here and in the corresponding factors inside here. So whatever relation we're going to get should be true for any tau. In particular, we can set tau to 0. So that would be convenient. The next step is to carry out the following integration. Say we want to get this particular one in terms of all those guys. So we choose to multiply by this and integrate over sigma. Remember, this is all done at tau equals to 0. Let me just remind you again. Very good. So we do the same thing on the other side. So we get 2ls squared. Of course, on the other side, all the modes will give us 0, except for m equals to n. So we will get L n tilde times the integral from 0 to pi of the sigma, which just gives us pi. Okay? So we conclude from here that ln tilde is equal to 1 over 2 L string divided by pi, this integral. Well, we could just sit down and do it, but it's actually trivial to do it. So we won't do it in detail. But we will just notice that that integral, if we look at the expansion, right, we have the expansion with the alpha tildes. So what are the only possible terms that can contribute that will give us a non-zero answer once we compute this, this integral? Well, imagine that from one of the factors in the square, we get some alpha m, right? So certainly it's going to be quadratic in the alphas, right? So we need 2 alphas. The Lorentz contraction will still be the same, so we will have something like this, right? Now suppose that this term didn't give us 0. So what should be the index of this guy here? Very good. It should be this, so that we get something non-zero from the integration. Okay. Now it turns out that the full answer is just the sum over all m's, and the normalization was chosen so that we just get a half. So that looks quite nice, but it looks even better if we use our notation. Sorry. And of course, we can get the same story for the left movers or the right movers. Yeah, so it will be the right movers. Now the constraints are simply that we should require this to vanish and this to vanish for all n's. Sorry, there is no tilde here. Very good. So let's look at the n equals 0 constraint. The reason is that that is the guy that contains alpha 0. And remember, from this computation, we learned that alpha 0 is related to the momentum in space-time of the string. So that should give us some information about the mass of the string. So we know from here that L0 tilde has to be equal to 0. That's one of the constraints. So let's write it explicitly. By looking at this formula, we get 1/2 alpha 0 squared tilde plus 1/2 of the sum But note the following. Here we have some double counting, right? Once we go from m equals to minus infinity to m equals to infinity, for every negative m, there is a positive m that will give us exactly the same contribution. So we could replace this sum by a sum over all positive m's Now we look at alpha tilde square. Go back here. Yes? Yes.
So if you're saying that every ln is 0 and every ln tilde is 0, does this mean that the expansion of the d plus xl, for example, is always 0?
No. No, this is a square, right?
Yeah, but I mean, you've got to consider
if you have a vector, right, and you say that the vector is null, does it mean that every component is 0? What we're asking is really that the vector del plus xl is null. Okay, so we have our friend there. Now from here we can compute what alpha 0 squared is. Well, it's just p squared over 2L string, the tension times pi. But p squared is the mass of the object. So let's use that formula over there and use that it has to be 0. Yes?
Shouldn't the denominator square?
The denominator. Yep. Thank you. Yeah. That would have given us a very funny formula in the end without the square. Okay. So this has to be equal to 0. And therefore, we learn that 1/2 m squared divided by, so that would be, so with the half, we'll actually get a pi squared, L string squared, times the tension squared is equal to the sum over the positive m's Okay. Now remember, we already had some definition for the tension. We said that it was 1 over 2 pi alpha prime. And if we now choose L string to be of this form, then we will find a nice formula. We will find that the mass for the closed string is equal to A times, I think it's, what is it that you get? It's actually a 4. 4 alpha m tilde dot alpha tilde minus m. Okay? Now, of course, we should have gotten the same thing, exactly the same thing, if we had done the L0. Okay? And remember, here I put a tilde, but we knew from the boundary conditions and the periodicity that the two alpha zeros had to be the same, the alpha tilde 0 and the alpha 0. So we get from that formula, we would get something exactly the same. But now for the oscillators without tilde. And this is the reason why some people like to write this in a more symmetric form. Okay, so this is a formula you will often see. Yes? Well, we only have one-dimensional parameter, one-dimensionful parameter, which is alpha prime, right? So this too is also convention, but that it has to be, remember, alpha prime had to have dimensions of length square, right?
Does this mean they can have massive gravitons?
Massive gravitons? Of course, we can have spin 2 objects that have mass, but they are not called gravitons. I mean, the name graviton is reserved for a massless, and remember, the representations are very different, right? Sorry? Oh, so the question is, would this mass condition be different at the quantum level? And the answer is yes, but just by a number, just almost in the most minimal possible way. Okay. Very good. So I think we're ready to move on to the quantization. So how do we quantize this thing? Well, it's a quantum field theory, really, right? If it was a one-dimensional, if it was the case of a particle, just like we did at the beginning of the second lecture, we will have some quantum mechanical system, right? But since we're doing the string, we have a quantum field theory in 2 dimensions. So in that case, usually in quantum field theory, we define the momentum conjugate of the field X to be something like this, okay? Now we have many fields, so you will have many indices. It's very hard to resist calling this thing, again, P, right, instead of pi. I mean, this is what you see in quantum field theory, right? Quantum field theory, you have pi, and then you have your momentum, and then you have your field phi, right, in quantum field theory. But it's very hard to resist the temptation, since this is our Lagrangian, it's very hard to resist the temptation of writing sorry? Here? Oh, sorry, in the Lagrangian, yes. Yes. Okay, so I hope it's not confusing that we're calling P everything that we see that looks like momentum, we call it P. Okay, so this P now depends on tau and sigma. Okay, so of course in classical field theory, the natural object to study is the Poisson bracket at equal times, but different positions. Can anyone remind me what this is? Remember, these are functional derivatives, right? Yeah, so there, of course there will be a delta mu nu, but then we also have the continuous analog, which is a delta function. Now here there is something special a little bit because our variables are periodic, okay? So since they are periodic, we have to be careful and use a periodic version of the delta function, okay? So our Poisson brackets are also defined using these functional derivatives, okay? So of course, these guys will give us 0. We have our P nu tau sigma prime. We will get eta mu nu, and we will get our periodic sigma prime. Okay. But from here, we can compute what this is. This is T x dot, right? Using our definition of the variations in the Lagrangian, we get this formula here. So we can replace this, if we want, by x mu x dot nu at sigma and sigma prime to be 1 over t eta mu nu delta sigma. Okay? So what could this periodic delta function be? Well, the last Poisson bracket that we need, of course, is P mu with P nu, which is equal to 0. So this periodic delta function is defined not as a Fourier transform. It's not the Fourier transform of 1, but it's the Fourier decomposition of 1 this time. Okay, very good. Let's see. So now we can plug in the modus function, because what we are interested in, after all, we have been learning that these fields look like an infinite collection of harmonic oscillators. These are oscillators, right? So what we want to do is to go from here to some algebra of Poisson brackets that look like the algebra of Poisson brackets for harmonic oscillators. So what we have to do is to plug in the expansion we had in these equations and get corresponding Poisson brackets for the oscillators. So that should be an exercise for you. And what you should find is that it's something like this. So I decided to use here curly brackets because that's the standard notation for Poisson brackets. But some people don't like to use curly brackets because they look like anti-commutators. Every time you see curly brackets, do you think about anti-commutators or not? Wow. So I should have used the other ones. I thought that still by you wouldn't be like so corrupted as to think that every time you see an anti-commutator, that you see curly brackets, they are anti-commutators. So we get two copies of the same algebra. And of course, modes in different sectors will give you 0. Now, using these Poisson brackets, you can go ahead and compute the Poisson brackets of the L's. And what you find is something very interesting, which you probably did already. Does this look familiar? It should. It looks like the algebra that Virasoro generators should satisfy in a conformal field theory. Okay. Of course, it's missing something. What is it missing? A central charge. But why don't we have a central charge here? Excellent. This is classical, so we still don't have any quantum corrections. Okay. Well, now let's do our quantization. Of course, Rob Specken will be very upset, but that's what everybody does. We take our Poisson brackets. Every time we see one, we replace it by a commutator. And we interpret these things as operators. That's our deep quantization of the system. Okay. But now, you see that if we do that, these guys almost look like harmonic oscillators, but not quite. What's the difference? Remember that, I mean, they look painfully close to harmonic oscillators. Yes, but there is something else that is slightly different. And that is a normalization, right? There is this M there. So if we just define, say, this operator to be 1 over the square root of M alpha M mu, and likewise A tilde. So now these are operators. Then we plug that in there, and we find we'll find a nice algebra for these oscillators. Of course, yes. Sorry? Well, that would only be a minus sign, of course. But so I think what I want to do is to multiply by I.
No, I mean, you want to take I H minus. You multiply the Poisson brackets by I H minus. So if you put it on the other side, you divide by I, multiply by minus I. If you say that the dots can be
well, try with both. Try with both. Try with whatever you want, and then see if you get If you get this formula, okay. This is the one we want to get. Okay. Now remember, we had the definition, we had the connection between alpha tildes and alphas, so that the field will be real, X will be real. Now that translates in the case of, in quantum operators, into the statement that this thing has to be the Hermitian conjugate of this field. Okay. Likewise, the same thing will happen for the A's. So if you wish, we have something that looks like well, let's see. If I do that, well, I really want to put here an n, say. I want to change this now to put an n. And if I do, then I have to say m comma n. Okay? Sorry. With the dagger. Yes?
I mean, that probably should be. No.
Okay, and then the same thing will happen for the tildes. All right, so everything is looking good. Now in the quantization, we have to define a vacuum to define our Hilbert space. And our vacuum is defined so that it's annihilated by all these operators. So we define A mu for A positive to be annihilation operators. Okay? And therefore, our friends here would be creation operators. So far, so good. There is nothing fancy, and nothing goes wrong. Yes? Well, so far, the two systems look like systems that are completely decoupled. It's like having two different sets of harmonic oscillators acting on the same vacuum. They annihilate, all the annihilation operators annihilate the vacuum. Okay? So it's like having two completely, two sets of harmonic oscillators. There is no problem with that, right? Well, they are the same object, but they are two different sets of harmonic oscillators, right? Okay, so as I said, so far so good. There is nothing fancy going on, or so it seems. But there is a problem already. So what's the problem? The problem is that let's study the following state. Imagine creating a state, anything you like, any m you like, but set or study the 0th component. Okay? So create a state by choosing the time component of some particular oscillator. Okay? Well, that doesn't look like a problem at the moment, but let's see what happens if we compute the norm of this state. What's the norm? Well, in order to compute the norm, all we have to use is this definition. So this will give us this times AM0, right? So this is the adjoint operator times AM dagger 0 But this is nothing but the commutator this guy with a 0 here. And now we see why we're going to be in trouble. Look at this formula. The commutator gives us eta 0, 0. So that's the norm of this state, which happens to be -1. So it's not looking good. Well, at least it's not looking as bad as it could have been if we had chosen the other signature. You would say, but well, okay, it's just one state. Big deal. Maybe we can just pretend that it's not there. Well, it's actually worse, much, much worse than that. So here is an exercise for you, which should be trivial. Take a state of the form. So a general state in the Hilbert space would be something of the form AM1, mu1, AM2, mu2, AM, say L, dagger, mu L, acting on the vacuum, right? For any L and any indices mu's and, okay? Now the exercise is to show that if an odd number of mu's are equal to 0, sorry, of mu's, right? These indices. Right? If you select an odd, if you choose any state, whatever you want, so that an odd number of these guys is equal to 0, then the norm of our state is negative. You'd say, well, big deal. We have an infinite number of negative of states with negative norm.
Can we mod them out like we do for minimal models?
Yes, well, certainly we could do it as we do it in CFD. But there is a physical reason why there are these states here, right? And a physical resolution for how to get rid of them. Remember, we're here just quantizing the free Lagrangian that we had over there. But we have to remember that there is something else we have to do, right? The constraints. We should not forget the constraints. This is just a Hilbert space that comes straightforwardly by just quantizing that action. We haven't said anything about the constraints. Well, we did before, but at the classical level. So we now have an infinite number of negative norm states okay? But we also have an infinite number of constraints so we should only hope that these two things match each other somehow, and that we can use this infinite number of constraints to project out the infinite number of negative norm states. So what are the constraints? Well, we wrote them down there. Of course, now the else become operators. So our L tildes and else are operators. And what would be the quantum analog of the constraints of saying that this had to vanish in the classical theory? Well, if they are operators, they can only act on the Hilbert space, and therefore the condition should be that these operators annihilate a physical state. Okay? But you see that there is something funny about doing this for all n's, positive and negative. The reason is that from the definitions we have over there, we see that if we have n positive, so maybe I should move this. If n is positive, this operator happens to be the adjoint of this operator. So we should only impose that this is equal to 0 for n positive, right? And now what is going to happen is that this condition will translate into this condition. For the negative else. Very good. The same thing should happen for the L tildes. They should annihilate all physical states. Now, when we go from a classical operator to a quantum operator, sometimes we are in trouble, right? Suppose that you have some classical object that is a product of x and p's, and you want to interpret that as an operator in the quantum theory. So you will be in trouble because there might be ordering ambiguities. And the only thing that we want to interpret now as operators are these L's. And these L's are products of alphas, which are these A's, or are related to these A's. So do you think we're going to have some ordering problems? Just look at the algebra. Is there any chance of getting an ordering problem? When do we have a chance to get an ordering problem? Right. So ordering problems will arise only for these two guys. The reason is that for any other one, remember this was defined to be something like this. And if m is different from 0, these two oscillators, these two operators commute. So we don't have any ordering problem. But if m is equal to 0, then we have to decide what to do. In particular, when this acts on a state in the Hilbert space, we cannot just say that this has to be equal to 0. How do we know? We don't even know how to define it. Of course, the only possible ambiguity should be in the commutator, right? On how to order these two guys. But any choice we make, or whatever is the correct answer, will simply give us, or will simply differ from any other one by a number, right? Because the commutator is just a number. So we can parameterize our ignorance of how to define this by simply saying that we decide to start out and defining the operator with a normal ordering, with the understanding that every time this operator acts on a physical state, we agree to allow ourselves to mess up by a little bit, by a number. Okay? So we choose a normal ordering as the definition of the operator, and then we allow ourselves to say that, well, since we don't know how to order it, but whatever different orderings will only differ by a constant, then we should allow the physical condition to be that L0 doesn't annihilate all physical states, but that physical states are eigenvectors of L0 with an eigenvalue, which is A. Now, since our system is symmetric, we should have the same normal ordering constant for L0 tilde. Whatever we do to normalize, to order this one, we should also do it for the L0 tilde, and therefore the discrepancy should always be the same number. Okay? So we see from here that what annihilates a physical state is the difference of the two operators. And this is sometimes called the level matching condition for the closed string. Which means that you cannot just excite some left movers without exciting right movers. There has to be some matching on the physical states. Okay? So you cannot just choose a state with only, just like I did here, you cannot just choose a state that only has left movers. That will not be physical. You have to compensate with the two. Okay? Very good. So I know that you probably won't be able to sleep with the tension that, oh my God, could this actually work? Could it be true that by imposing these constraints, we're going to get rid of all these infinite norm states? But I'm afraid we ran out of time today, so we'll have to do it tomorrow. Yeah, but so that you can sleep, the answer is yes, we're going to be able to do it. But we're going to have to pay a price for that. Which is that this A is going to be fixed, and also the number of scalar fields is going to be fixed. Only when the two things take particular values, we will be able to kill all these infinite negative norm states.